Hi, and welcome to the slideshow on how to interpret ANOVAs and regressions. I really wish that we could do this in person and use SPSS, but we can't. So this slideshow is going to talk about mostly how we'd go through and interpret and examine ANOVA and regression tests. So we talked about this in class the Friday before spring break. And we actually ran an ANOVA that day. To remind you, ANOVAs are short for analysis of variance. This test determines if there's significant differences between the means of 3 or more groups. You can do it when there's only 2 groups, but most of the time we would just use an independent sample t-test for that. ANOVAs have an independent variable that is nominal or ordinal, and a dependent variable that has to be scale. And again, we're looking for differences in the means between 3 or more, or occasionally 2 or more groups. So here, click on this link and listen to how we interpret ANOVAs. All right? This video is about 15 minutes. It does a very good job discussing how to interpret ANOVAs. As a side note to this video, or as an addendum, I guess I should say, we always report the means and the standard deviations for each group that is being compared in the ANOVA, both when the test is found to be significant and we are rejecting the null hypothesis, and when the test is not significant and we thus fail to reject the null hypothesis. So here's the problem. Let's say that a researcher is investigating whether delivery type instruction affects a student's scores on an exam. Some of the students who took an exam attend lectures in person and they're given the code of 1. Some of the students who took an exam attend lectures online and they're given the code of 2. And some of the students who took an exam attend lectures both in person and online and they're given the code of 3. So based on this data, can we be 95% confident that students scored differently on the exam based on how they received instruction? How would we know to run an ANOVA on this problem, on any problem? The biggest clue would be that we're looking for differences in the means of 3 or more groups. Again, we also have to have a problem where the independent variable is nominal, or it could be ordinal, but in this case, the problem is the independent variable is nominal, and the DV is scale, it's exam scores. Step 1, just like for every other problem, we first need to state our hypotheses. So take a guess on what your hypotheses are going to be and write them down now. Here are your hypotheses. The null is how students received instruction did not affect exam scores, and the alternative is how students received instruction did affect exam scores. Step 2, we'd run the test in SPSS and we'd get a printout for it. Here's a photo of the printout from this test. Step 3, we need to figure out what's important on that output. We need to interpret that output. So if you look at our descriptives, the means and standard deviations for each group are what's important. In-person instruction had a mean score of 78.0 with a standard deviation of 5.735. Online instruction had a mean score of 86.40 with a standard deviation of 3.098. And hybrid instruction had a mean score of 93.60 with a standard deviation of 2.951. Under the subheading ANOVA, what's important is the degrees of freedom. Between groups, degrees of freedom equals 2. Within groups, degrees of freedom equals 27. And total degrees of freedom equals 29. The F statistic is also important, and that equals 35.719. And the significance is important, and that equals 0.00. Because the significance of 0.00 is less than the alpha of 0.05, we would reject the null hypothesis. So what's important on that Tukey's output? Well, Tukey's outputs and all of the ad hoc or post hoc tests are a little bit difficult to interpret at first. First, the outputs are comparisons between groups, and they designate which groups have statistically significant differences by asterisks. We need to interpret the groups that have asterisks next to them. If something doesn't have an asterisk next to it, it doesn't need to be interpreted. But at the same point in time, Tukey's outputs also compare the outputs twice, essentially, or make the comparisons twice to each other. So note that the comparing method 1 in the I column and comparing to method 3 in the J column, it has the same result as comparing method 3 in the I column and method 1 in the J column, except the sign is switched. So essentially, for every significant comparison on a Tukey's result, it's going to print out twice on the results, but you only need to interpret one of those. So if we look at the results of this specific comparison, when 1 is in the I delivery method column and 2 is in the second J delivery method column, the mean difference is a negative 8.40. This means that students who received in-person instruction had a mean score 8.4 points lower than students who received online instruction only. When 1 is in the I delivery method column and 3 is in the J delivery method column, the mean difference is a negative 15.60. This means that students who received in-person instruction had a mean score of 15.6 points lower than students who received the hybrid instruction. And when 2 is in the I delivery method column and 3 is in the J delivery method column, the mean difference is a negative 7.2. This means that students who received in-person instruction had a mean score 7.2 points lower than students who received hybrid instruction. The final step is to draw conclusions, and so our paragraph would look like this. We computed a one-way ANOVA comparing the type of delivery instruction a student received to the student's exam scores. A significant difference was found among instruction types. F of 227 equals 35.719 or 0.72. Probability is less than 0.05. Tukey's was used to determine the nature of the differences among instruction types. Students who attended in-person only classes had the lowest score with a mean of 78.00 and a standard deviation of 5.74. Students who had online-only classes had a mean score significantly higher than students who attended in-person only classes with a mean of 86.40 and a standard deviation of 3.10. Students who received hybrid instruction had a score significantly higher than that of students in both of the other groups with a mean of 93.60 and standard deviation of 2.95. So, those significantly's in the conclusion indicate where the asterisks were on the Tukey's printout. So let's try that again with a new scenario. A researcher is testing whether 3 different medications relieve patients' pain levels. Can we be 95% confident there are different levels of pain relief? Step 1, write the hypotheses. Go ahead and write them down now. Step 2, sorry, I didn't mean to go to step 2. Here are the hypotheses. The null is that medicine type does not affect pain relief, and the alternative is medicine type does affect pain relief. If you were wondering how you determine whether to run an ANOVA here or not, you'd say, I would run an ANOVA here because my independent variable is nominal, my DV is scale, and I'm looking for differences in the means of 3 or more groups. Step 2, I would run my SPSS run my test in SPSS. Here's what my output would look like. What's important on that output? You need to interpret it. Try your best right here. So here's what you should have interpreted. The mean for the first medicine has a relief score of 6.20 with a standard deviation of 2.168. The mean for group 2 is 4.60 with a standard deviation of 1.673. The mean for group 3 has a relief score of 5.80 with a standard deviation of 3.493. The degrees of freedom between groups, degrees of freedom equals 2, within groups equals 12, and total equals 14. The F is 0.528. The significance is 0.603. Because the significance is greater than the alpha level of 0.05, we would fail to reject the null. And because we failed to reject the null, we don't need to run it 2 keys. But we still have to draw a conclusion, and that's step 4. So we ran a one-way ANOVA concerning the amount of pain relief patients who took 3 different medications received. No significant difference was found. F of 212 equals 0.528, and we failed to reject the null hypothesis. The amount of relief patients experienced did not differ significantly based on the type of medication received. Patients who took medication 1 had a mean relief score of 6.2 with a standard deviation of 2.17. Patients who took medication 2 had a mean relief score of 4.60 with a standard deviation of 1.67. Patients who took medication 3 had a mean relief score of 5.80 with a standard deviation of 3.49. The last test that we'll learn is simple regressions, and we need to distinguish simple regressions from multiple regressions or complex regressions. Multiple and complex regressions are the same thing. In simple regressions, we have one scale independent variable, and we're looking at its effects on one scale dependent variable. In multiple or complex regressions, we have many independent variables, and we're looking at all of their combined effects on one single dependent variable. So all we do in this class is simple regressions, but you need to know that multiple regressions exist. As I mentioned, regressions have a scale independent variable and a scale dependent variable, the kind of regressions we study. They are also the only test that we learn that you can use to predict an outcome for data that you don't have. So you can use the data you have to predict outcomes for data that you don't have. That's actually how they're predicting infection and death rates for coronavirus right now. They're looking at data from Italy and comparing it to data from the US. And they're using the data from Italy and combining it with data from the US to use regression analysis to predict infection rates and morbidity rates. So the next thing that you need to do is watch the video on interpreting simple regressions that's linked to below. So go ahead and do that now. Let's talk about some scenarios where we would need to run regressions. Guess how we're going to start? We're going to start with hypotheses. So in the scenario that's described above, which is can we be 95% confident that as height measured in inches increases, weight measured in pounds increases, we need to come up with some hypotheses. Null hypothesis is the hypothesis of no relationship. So it's going to be that height is not a predictor of weight. The alternative to that is that height is a predictor of weight. What am I going to do next? I need to run the test in SPSS. You don't need to do that, but look, here's some SPSS output after I ran the test. Step 3, we need to figure out what's important about that information that SPSS gave us in our output. We need to interpret it. So under the model summary, if you look under the model summary output on the previous page, you can see that our R square is equal to 0.396. If you look under the ANOVA output, it says the degrees of freedom regression is equal to 1, the degrees of freedom residual is equal to 18, the degrees of freedom total is equal to 19, and then we need to look at our test statistic. In this case, our test statistic is an F statistic, and that's equal to 11.78. Our significance for our F statistic is equal to 0.003. Our alpha level is 0.05 because we wanted to be 95% confident. But since our significance of 0.003 is less than our alpha of 0.05, we reject our null hypothesis. Because we reject our null hypothesis, that means we have to interpret the coefficients for our regression. So to interpret the coefficients, we look at the coefficients output, and we see that there is a constant beta, or constant b, and that's equal to negative 65.242. Then we have the height, b, which is equal to 3.245. Using this info, we can create a regression line. Remember way back to middle school or high school math and the basic equation for a line. The basic equation for a line is y equals mx plus b. And guess what? That's also the basic equation for a regression line. Y equals mx plus b. So, with the above coefficients, the equation becomes weight, which is what y is equal to, or what y is standing in for, is equal to 3.25, which is 3.245 rounded to the nearest hundredth. So 3.245 times x, x is whatever the height is, plus a negative 65.24. So that full equation is y is equal to 3.25x plus a negative 65.24, or weight is equal to 3.25 times x, where x is equal to the value of height plus a negative 65.24. This equation means that for every 1 inch increase in height, we expect weight to increase 3.245 pounds, or weight to increase 3.25 pounds. The next thing we need is a conclusion. So here's what the conclusion would look like for this problem. A simple linear regression was calculated to predict participants' weight based on their height. A significant regression equation was found. F of degrees of freedom 1 and 18 equals 11.78 with a probability of less than 0.05, with an R squared of 0.396. Based on this, we reject the null hypothesis. Based on these participants, the predicted weight for a person is equal to 3.25 times the person's height plus a negative 65.24, where height is measured in inches and weight is measured in pounds. Participants' weight increases 3.25 pounds for every inch of height. Let's try that again. Here's a new scenario. The variable urban population is the percentage of a state's population that lives in an urban area. The variable assault is the number of assaults reported to the police per 10,000 residents of a state. Based on the information given, can we be 95% confident that as percentage of the population of a state living in an urban area rises, assault rate for the state increases? We would run a regression here because we are looking to see if one scale variable increases as another scale variable increases. Guess what we're going to do? First step is hypotheses. So right now, write your best guess for hypotheses down. For this problem, the null hypothesis would be urban population is not a predictor of assault rate, and the alternative hypothesis would be urban population is a predictor of assault rate. Next, we'd run the test in SPSS. I've done that for you, so voila, there's output below. The next step would be to interpret that output. So pause the slides here, go back and look at that output, and do your best to interpret the output before moving forward to the next slide. What's important about this output? Well, here's the interpretation of it. Under the model summary, the R squared, or the percent of variance in the dependent variable that the independent variable explains, is equal to 0.067, so it's a very small percent. Under ANOVA, the degrees of freedom regression is equal to 1, the degrees of freedom residual is equal to 48, the degrees of freedom total is equal to 49. The F value is 3.45, and the significance of that F is equal to 0.069. Since our significance is higher than our alpha level of 0.05, we fail to reject our null hypothesis. Because we fail to reject the null hypothesis, we do not need to interpret our coefficients or come up with an equation for the regression line. So step 4 is our conclusion. Pause the slideshow here and do your best to write a conclusion before you move on to the next slide. Here's our conclusion. A simple linear regression was calculated to predict states' assault rates based on states' population that lives in an urban area. The regression was not significant at the alpha equals 0.05 level. We failed to reject our null hypothesis. The F of 148 degrees of freedom is equal to 3.448 with a probability greater than 0.05 and an R square of 0.067. Urban population is not a significant predictor of assault rate. And that's it. Thank you for attending this. Don't forget to take your quiz on Canvas. Homework number 7 is live in the homework number 7 folder. It's due next Friday, 4/3. Feel free to call or text me with questions. And don't forget to stay safe. I miss each of you, and I hope that things are going okay. Let me know. Talk to you later.